Oh, wait.
Am I the first one?
I think so. Yeah.
Yeah.
Okay.
Okay, and we're live now.
Okay. We're going to go ahead and get started right on time here. No reason to delay. So let me just give just a few words of introduction. Jimmy Zhu is an IEEE fellow and is a full professor at the Department of Electrical Computing Engineering at CMU. And is an endowed chair in the College of Engineering. Has been in the field of magnetic data storage, and so he's you can see his title there. He's going to be presenting, and he'll have 15 minutes, and then we'll do 5 minutes of Q&A after that. So go ahead.
All right. Thank you very much, and thank you for inviting me, and appreciate it. So today I'll talk about the work one of my students did on iridium-enabled field-free spin torque, orbital torque switching of perpendicular MTJs. So, right, so I'll get right onto it, all right. So just a little bit of introduction of the spin orbital torque. And so we're talking about the spin Hall effect in heavy metals. And so you have if you have a ferromagnetic thin film on top of a heavy metal layer, and you inject the current, and the spin Hall effect, and that inject the spins into the ferromagnet, and in this configuration, and the inject spins actually are horizontal. So so usually when people first discover this spin Hall effect, they use it to switch in magnet, the little tiny magnet is really switching the in-plane devices, right? So because the injector spin has a horizontal orientation. So so here we really wanted to switch a perpendicular MTJ. So if you have a perpendicular magnet layer on top of these heavy metals, and then you inject the current in the heavy metal, it really doesn't switch the perpendicular magnet because of it's a symmetry, and it really doesn't matter whether the magnet moment in the ferromagnet is up or down, right? It's perpendicular. So you need something to break the symmetry, and in order to switch it. So what people do is to apply in-plane magnetic field. So if you apply in-plane magnetic field, you would be able to switch it. If you apply in-plane field along the current direction, of course, depends on the spin Hall coefficient of the heavy metals. And then you apply in-plane field. In one direction, you'll spin the up to down, and the other opposite direction, you'll spin down to up. Okay. So so this is the nature of the spin orbital torque and the spin Hall effect in particular. And so therefore you need, usually people apply external field and try to switch the perpendicular magnetic devices. So so here we're trying to use, to not have the hassle that we have to apply external in-plane field, but rather to build this in. So what we want is, if we have a heavy metal layer that can have some sort of can facilitate in-plane coupling, not only generate a spin Hall effect, but can also facilitate the in-plane coupling. So if we have a in-plane magnetic field, film underneath, and then if there's interlayer exchange coupling that can be facilitated by this heavy metal layer, then we can apply this built-in in-plane magnetic field. So that's the thought, and one of these materials is uridium. Okay, so so the uridium not only is a heavy metal, can produce can have the spin Hall effect, but you also have can facilitate the in-plane exchange coupling. So so here is the experimental study we have done. So here is a uridium film, and that's about 1.3 0.35 nanometer thick. Actually, will vary the thickness of the iridium film. And then we have two in-plane cobalt layers and sandwich on both sides. So if you measure this structure, then you can see this very strong in-plane coupling, and that resulted from this iridium layer and in between. So this iridium interlayer, that if it's thinner than 8 angstroms, is thinner than 8 angstroms, somewhere around 6 angstroms, and you actually see very strong antiparallel coupling. But we're not using that peak because it's too strong, and we sort of use the second peak, which is relatively weaker. Okay, so that second peak occurs at about 1.3, 1.4 nanometers, right? Okay, so so that's the film study, and so we build, and so when we did this, we build a Hall cross. So you have you measure the Hall voltage on this Hall cross, and to measure the magnetic switching, right? So the perpendicular layer here is the iron cobalt boron. So you then spotted iron cobalt boron on top of uranium, you actually get this perpendicular anisotropy if you put an MgO layer on top of it and near it. Okay, so so here is the whole structure of the film. We'll have an antiferromagnetic layer underneath here, and then we'll have a SAF, and that's cobalt, ruthenium, cobalt, and that's an in-plane synthetic antiferromagnet. And then we have a uranium layer, so therefore you have this in-plane layer next to the uranium layer, and then you have a perpendicular cobalt and boron, and then with the MgO on top, and that gives rise to a perpendicular anisotropy to the iron cobalt boron layer after annealing, right? So you can see from the film level measurement, you can see the iron cobalt boron has a perpendicular anisotropy, and you can see the in-plane, the red is the in-plane measurement. So you can see, sort of see what's the anisotropy constant, right? So, and the insert here is a blow up this perpendicular loop of the iron cobalt boron. Okay, so you do this measurement and the Hall measurement, and you send a current in. So the horizontal axis here is the current flowing in the uranium layer. Of course, it also flowing every other layers, but it's the flowing in the uranium layer generates the spin Hall effect. And so you can see, you can have the perpendicular switching, and all these curves are corresponding to a different in-plane magnetic field. So we do apply an in-plane magnetic field, but the important thing is this black curve is when the in-plane magnetic field is 0. Okay, so you can see if you switch the direction of the in-plane field, the switching polarity changes, right? But at 0 field, you can get a very nice perpendicular switching. And by applying an in-plane field, you can also test that what is the exchange coupling field, and that facilitate this switching. Because around 200 oerstats or 150, and the whole switching collapse. So you sort of can tell what's the exchange coupling field that's facilitated by this iridium layer. Okay, so right, so this is just right. So then what we did is we built a whole 4 film stack and try to fabricate a magnetic tunnel junction. So you can see the top structure here is the pinned layer. So the top iron cobalt boron layer is a pinned layer that's on top, deposited on top of the MgO layer. And so you have a phase breaking titanium layer with a SAF that's formed by cobalt platinum multilayers. And then you have a uranium, you have a ruthenium layer in between. So this build a perpendicular SAF, synthetic antiferromagnet, and that provides the reference layer for this top cobalt, iron cobalt boron electrode. And then the bottom one is the free layer of the iron cobalt boron. Basically, that's essentially the same structure we just talked about for the spin Hall cross, for the Hall cross. And so you have this 1.2 nanometer magnesium oxide tunnel barrier, right? So that's the film, and that's the film measure the ionization, perpendicular loop, in-plane loop. So you can see this is the ZAP, and that's the free layer switching, okay, and in the middle, right? So and then we went on pattern this. We pattern the MTJs, and the size, the diameter of the MTJs varies from 150 nanometers to all the way down to 50 nanometers. So if you look at this is a electron microscopy picture, SEM picture. So you can see this is the bow tie structure is the bottom iridium layer stack, and that is the spin Hall structure. And this is 10 micron, and that's actually as one of the challenges, and to make this very small it's not easy unless you have a CMP technique, right? So then we patterned the MTJ on top of it, right? You can see this is the cross section, and you can see the MTJ, and you can see the magnesium oxide layer. We stopped at the magnesium oxide layer, and there's a little step here, and right, and that's it's tough to do this ion mill. So so then we put on a top gold electrode, and that's the gold electrode on top of the MTJ. Okay, so if you look at the field switching, and you sort of see the MTJ we have in the device level at the 50. This is a 50 nanometer, 150 nanometer MTJ device, and it has about 60% TMR, right? So it's a nice switching, but this is a field switching. Okay. So then what we did is to hook up the MTJ to use a locking amplifier to look at the MTJ resistance change, and then the horizontal axis here is the current flowing in the bottom spin Hall structure, right? So it's in the bottom iridium stack, right? So so you can see this is the current, and the vertical axis here is the resistance through this locking amplifier measurement, and look at the MTJ resistance. So you can see we can very nicely, repeatedly switch the MTJ using the current flowing in the iridium layer. So this is B-orbital torque coupling, and this is without any applied field. So there's no field applied, and that so therefore is really this in-plane exchange field facilitated by the iridium layer, and facilitate this spin Hall perpendicular switching. And one of the challenges we had experimentally is we can't make the pulse width too short. Okay, and I'll elaborate this later on. So we vary the pulse width actually, and we like to have this pulse width below a nanosecond, but it's very challenging to do that. So right, so this pulse here is 200 nanosecond. Now, of course, we can do shorter, and I'll show you later on for the results. And then, so here is a repeated switching. So you can see we repeated number of pulses, and then you do the measurement, and so you can see a very repeatable switching, and the resistance variation is not that much at all. Okay. And,
we have about 2 minutes left.
Oh, my 2 minutes left. Okay. All right. I'll skip some of this. Okay. So then we did some micromine modeling, and to see how this MTJ switches, right? So this is a micromine modeling of this MTJ switches, and then so the yellow is up, and the blue is down. So you can see the device actually switches with these stripe domains, and then the stripe domains will expand, and that result in the entire device switching. So, but I do want to I want to skip this. So therefore, if you make a comparison of the switching by micromagnetic simulation and the measurements, and you find this is the comparison. Okay, so So the horizontal axis here is the inverse of the pulse width, right? So the shorter pulse width is towards the right, the longer pulse width towards the left. And you can see these red dots are experimental measurements, and this is the black curve is the calculation. So they are very not agree to each other at all. So what happened, I think, actually, is this heating, because the shortest pulse width we did, if you look at this measurement, the shortest pulse width I did is over 10 nanoseconds. Okay, it's about 20 nanoseconds, and so therefore, during that 20 nanosecond, the wire heats up, and so the MTJ free layer also heats up. When the MTJ free layer heats up, the anisotropy dramatically goes down. So this is the experimental measurement of anisotropy in the iron cobalt boron and versus temperature. So right, so you can see 100 degrees C above the ambient temperature, above room temperature, the anisotropy already reduced significantly. So if you take this into account and calculate and try to fit the experimental results, you find that if you lower down the anisotropy of the free layer MTJ and redo this micromagnetic simulation, so that's the curves, you can see the circles, the open circles plotted in here. So what we think is that in all this spin Hall measurement, the thermal effect actually dominates. And it's hardly you can measure the intrinsic switching. All you measure is really the reduction of the anisotropy in the free layer. Same thing is true for the STT MTJs, right? As long as if your pulse is not shorter than a nanosecond, and you're always going to get into this thermal region that heats up the device and reduce the anisotropy significantly. Thank you.
Okay, well, I guess we can't hear any applause, but we all thank the speaker. Let's go ahead and open it up for questions. So there are some that can be relayed from YouTube, and there are some live participants also. So if there are any live people who want to jump in at this point with questions, feel free. I'll just ask a very basic question to start us out. So what is it actually that controls the intrinsic time constant for the switching time physically?
So physically, it's really the precession of the spins in the influence of a combination of the spin Hall torque and also this in-plane field. And that two combination and really is the precession of the spins that determines the switching time.
And that's of the order of a nanosecond.
That's the order of a nanosecond, right? You can see that, right?
Okay. Are there other questions?
Yeah, I have one question.
Yeah.
Very nice talk, Jimmy. So
thank you.
So when you're talking about this exchange coupling across this iridium, right?
Yes.
So I think on your slide 3 or 4, you showed how this exchange coupling decays as a thickness, right?
Right. Yes.
And you pick up right here. So you pick up around 1.3 nanometers. So naively thinking, I would think that this exchange coupling will decay as a function of this thickness, but somehow around 1.3 nanometer, you see this increase in this exchange.
Right. So yeah. So this is the RKKY type of coupling, right? So you're oscillatory. So it oscillates. So usually you see a few more peaks, but usually the further, the thicker, the smaller the peaks, and decays really fast. But it is oscillatory.
I see. And then I think because you are relying on spin orbit torque, right, coming from spin Hall,
yes,
you want this thickness of radium so that you have enough charge current flowing through.
Correct.
I see.
Yeah.
Great.
It's really a compromise of the two. Yeah.
Thank you.
Thanks.
We have time for one more question.
I've got a quick question, if that's all right.
Mm-hmm.
So you have these stripes generated in your modeling in slide 13.
Yeah.
But you also have the resistance fluctuation on 11. I think you just passed it as a number of cycles. Is this fluctuation in the resistance read levels due to these stripes generation and degeneration, or is that device degradation?
No. These stripes formed is during the process. So what it is usually in this perpendicular MTJ, you have a perpendicular anisotropy, right? So it's easy to switch this way. It means you always have up and down, up and down, up and down. So magnetically, that's easier. So yeah.
Okay, thank you.
No problem.
Okay, well, I think for sake of keeping on the schedule, we should move on.
Thank you very much.
Yes, thank you. And is our next speaker actually with us?
Yes, I'm here. Yeah.
Okay, good. There we go. All right. So let's go ahead and go on to this talk. Do you have your slide? Okay, very good. Okay. So let me read just a short bio for Xiaodong Xu. He's professor in the Department of Material Science and Engineering and the Department of Physics at the University of Washington. So this is a non-local interaction. His research interests include optical, electronic, and quantum properties of novel solid-state nanostructures with device design, electrical spectroscopy, electrical transport, scanning, photocurrent measurements, and is a recipient of the Department of Energy Early Career Award and the NSF Early Career Award and the DARPA Young Faculty Award. Without further ado, go ahead, and you will have, this will be a half-hour talk with plenty of time for questions at the end. So thank you.
Thank you for the invitation. And today I'm going to talk about one of my favorite topics on Moiré excitons. So before I go into talk, right, I just want to motivate a little bit about why we work on this. So in solid-state systems, we all know, right, the crystals are formed by arrays of atoms in these periodical structures. So here I show you the simplest example of 1D atomic lattice. Then in these type of systems, we know that the physical property really determined by these lattice constant, by these periodical potentials, right? So with this periodical potential, we know the electron will have these block wave functions. So basically a plane wave without these periodical potentials, and then time these block wave functions. These periodical potential induced these wave functions. So we know that if we can control these fundamental parameters in these solid-state systems, such as these periodical potentials, a lattice constant, then we can really control the physical property of solids and engineer all kinds of physical properties, states, etc. But in reality, right, to control these fundamental physical property actually is quite challenging for a given crystals. And analog to such control is done in atomic systems, right? For example, here I show these optical lattice, and you can use the interference beams to create these traps, and the researchers can load these dilute atomic gas, right, atoms into the systems, then do quantum simulations of condensed matter systems. So this is really nice, actually advanced. And the question I want to ask is, well, how can we do similar things in solid-state systems, right? And to make a real advantage of these devices controls. So the opportunity is provided by these 2D materials. Here I give you example, a single sheet of carbon atoms, graphenes, right, has these hexagonal lattice structures. And many of us knows once you stack this graphene on top another 2D material, so on top itself, and with a little twist, you can form these periodical lattice structures called Moiré superlattice. Now we know that for these Moiré superlattice, we can control these Moiré potentials and control these superlattice constant by control these trace angle, or for example, what the substrate we're going to put on, right? So simple example is once you put a graphene on top of hexagonal boron nitride, and then the band structure will be significantly modified. In addition to these Dirac point, there's a secondary Dirac point going to form due to these Moiré superlattice structures. And very recently, everybody knows these famous twisted graphing systems, right? Once you have a two-sheet graphing from these magic angles, you can observe all kinds of correlated electronic states, superconductivity states, etc. So the work, mostly started and focused on these graphing systems, and actually there's all kinds of different 2D materials, and there are also Moiré superlattice potentials on these different 2D material systems. One of my favorite systems is transition metal dichotomized, which is semiconductors. So early research already shows when you stack two different transition metal dichotomized on top of each other, it's also form a Moiré superlattice with periodical potentials. So here's an example I showed down by my friend Ken Shi's group at UT Austin. And he studied used the STM and STS measurements of these MOS2, WSE2 heterobilayers. And he observed these very clear Moiré patterns. And if we take line cuts right across these high symmetry points, and you will see these band gap actually significantly modulated right as we across these lines. So the take-home message is in these TMD heterobilayers, actually the Moiré superlattice potential are going to significantly modulate these band gap and create these Moiré superlattice in the real space. And taking these opportunities, right, the question we'd like to ask is, well, given these Moiré superlattice potentials, can we trap electron hole pairs right in the systems? Basically, as I show here, this is excitonic lattice. And then by control the lattice constant, etc., by control the charge dopings, then we can form these excitonic lattice, but controlled by light. And this field actually advanced also real fast in the last couple of years. There's a lot of work being done to study these exciton trapped in the Moiré superlattice potentials. We call Moiré excitons. And I apologize if I missed any citations here. But the point is, a lot of work being done, and there are many interesting actual phenomena being observed associated with these Moiré superlattice potentials. And then in the following, I'm going to talk about the work done in my group. And the system we focus on is called MOSE2, WSE2 heterobilayers. And the reason we started with this system actually many years ago is because my group found for Monolayer MOSE2 and also Monolayer WSE2 itself produced really clean optical spectra. So it's a highly tunable excitonic system in the Monolayer limit. So the thought we have at that time is, well, let's just put these two clean sheets on top of each other, see what we can get. But it turns out, when we put the MOSE2 and the WSE2 on top of each other, they form these type 2 band structures. Okay, so what it means is lowest energy conduction band is in MOSE2 and the highest energy valence band in WSE2. So when the optically excited electron hole pair in the system, the electron going to go to the lowest energy conduction band. In this case, will be MOSE2, and the hole will go to the WSE2. So we have a spatially separated electron and hole pairs. And these electron hole pair, they're going to talk to each other through Coulomb interactions. Then we're going to form these so-called interlayer excitons or spatially indirect excitons. And luckily, for the system, is the lattice mismatch between these two monolayers is quite small, actually 0.2%. So this means is we can create a Moiré superlattice as large as 150 nanometer in terms of Moiré wavelength. So we started this project back to 2013 actually. My student Pasqua, he started to fabricate these heterostructures. Here's the first generation the device we made. Optical image shows this Monolayer MOSE2, Monolayer WSE2, and with this heterostructure area. And then we perform photoluminescence measurements. So first we look at the luminescence from this Monolayer WSE2, and then we see these just intralayer excitons. And we can do the same measurements on Monolayer MOSE2 and see the intralayer exciton itself. Then when we shine light on this heterostructure area, right, we show these 4 peaks, which is resembles these exciton from individual monolayers. Then we see these interlayer exciton feature at the lower energy, right? This is coming from the electron hole recombination, in opposite layers. So later on, many groups, including us, already improved the device, and this is what the clean heterobilayer are going to look like. Right, the interlayer exciton emission actually is strongly suppressed because of the efficient interlayer charge hoppings, and then the interlayer exciton actually dominated the optical spectroscopy. So what I told you now is the Interlayer exciton property is very similar to a couple of the quantum wells, right? Many people already done this for many years. There's a new feature in these double monolayer system is where they inherit the spin and the valley physics from individual monolayers. So my friend Disha and Wang Yao, they developed these theoretical foundation to understand the system. So basically, in the monolayer TMD, they have these 6 derived cones, and due to these inversion symmetry breakings, right? These 6 cones, 2 of them actually are not degenerate, right? Has plus K and minus Ks, and the individual values can be selectively addressed by circular polarized light. So these give us the first solid state systems with optical, addressable values. So with such a systems, and now we can plot these band structure in the momentum space for the heterobilayer. So on top, I have these conduction bands from these MOX2, so MOSE2 basically, and then the bottom is from WSE2. There's a valence band. Now we can imagine, right, if we put electrons in the K value in MOSE2 and the holes in another K value in WSE2, then these interlayer exciton, they're going to inherit these value index, right? So we can create these interlayer valley excitons. So we demonstrated such interlayer valley excitons by optical, circular polarized optical excitations. The hallmark is the light emission will be co-circular polarized with the excitation light. So for example, in this case, right, we excite the system with sigma plus polarized light, and then we see the light emission is dominated by sigma plus emissions. So we're gonna go back to this property a little bit later. Okay, so an interesting property of these heterobilayer is, right, I already showed you, the structure in the momentum space. And here's a little angle theta here, which is twist angle. And you can imagine, right, in the momentum space, when we increase this twist angle, then the values in the conduction band will start to misalign with the value in the valence band. Then the optical property will be changed, right? The simplest example is when these electron and hole are not aligned in the momentum space, they will become highly momentum indirect. Then the interlayer exciton recombination will be strongly suppressed. So we examine such a possibility to fabricate such a sample, right? As I show you here is the atomic force microscopy image of a monolayer WSE2 and on top of monolayer MIC2. And the sample is fabricated in one step. So we basically use this Terra stack method, back to 2016. And we can fabricate the sample with these 2 different twist angles. Actually, one is 2 degree, the other is 20 degree. So the first thing you observe is, well, with these, if we look at these interlayer exciton emissions, right? For this 2 degree sample, the emission is much stronger than these 20 degree sample, right? This can be understood as I just told you. In a 20 degree sample, the twist angle is larger than the interlayer exciton becomes highly momentum indirect. Therefore, the interlayer exciton emission is strongly suppressed. The other interesting property is we look at the interlayer exciton emissions, right? For the 2 degree samples, right, the interlayer exciton emission is strongly suppressed. But for the 20 degree, actually, it's pretty strong. So we know that in these heterobilayer systems, right, and when you photo-excite these electron hole pairs, the interlayer hopping, the electron can transfer from WSE2 to MIC2, and the hole will the other way around. And these electron transfer between layers actually will compete with the electron hole recombination in the monolayers. Therefore, if this transfer rate is much larger than the electron hole recombination rate in monolayer, the this interlayer exciton emission will be suppressed. That's happening in these 2 degree samples. But in the 20 degree, clearly, right, we can observe very strong interlayer exciton emission. So what it means is, in this case, the interlayer charge hopping rate actually is comparable to the electron hole recombination in the monolayers. Therefore, by tuning this twist angle, actually, you can significantly adjust or tune these interlayer charge hopping rate. And when my student first showed me the sample, when he showed me the data, right? And if you pay attention to the spectra, you will see there's a lot of kind of a narrow lines on top of these broad spectras. And when we start this project, we want to look at these twist angle dependent properties. And when I see these very narrow lines on top of these broad background, I thought the sample was not clean. So my student was kind of disappointed. And when look at these AFM image, actually it's really clean. There's no bubbles, there's no dirt, but somehow the spectroscopy feature shows it's not clean. So we don't know what to do. And then we talked to our theorist, and Wang Yao, and what he basically.
I'm sorry, I have a quick question.
Yes.
So in the previous slide, so what is the spot size that you're looking at?
The laser spot size?
Yeah.
Yeah, the laser spot size is about the 1 micron scale.
I see. And the positions of those peaks, is it the same if you move the spot by 1 micron or 2 microns?
Roughly the same, yes. I mean, the exact position will change, but the overall feature will be similar. You will see a lot of little things sitting on top of these broad things. Yeah.
Okay. All right. Thanks.
So yeah, well, we'll show you a moment what's happening here. And when I talk to Wang Yao, right, imagine, we have these Moiré superlattice potentials. If we zoom in on one potential, will look like that, right? They have these smooth trapping potentials. And imagine if we only excite one exciton in the system, then these exciton going to trap in these Moiré superpotentials, right? Then the system will behave like a quantum dot. So the first thing we should see, actually, if there's a Moiré exciton, is we should see the quantum dot-like photoluminescence. And the difference between these Moiré superlattice potential compared to quantum dots is because these potential actually will inherit these. They will have these high symmetry point, right? They will inherit these crystal lattice properties from the individual monolayers. So here I show you 3 high symmetry point, and due to these local crystal symmetries, then the Interlayer exciton will have distinct optical selection rules. For example, right, they can have a co-circular polarized, they can have a cross-circular polarized, or they can have a maybe linearly polarized. Okay, so when I say these cross-circular means, when I excite the system with sigma plus, the light emission will be sigma minus. And so the take-home message is, if we want to look for these Moiré excitons, we should pay attention to 2 things, right? One is we look for quantum dot-like photoluminescence. The second is we look for this valley-dependent physical property, which inherited from individual monolayers. So then my student go back, redo the experiment, because I told you, right, we want to load just 1 exciton or minimum number of exciton in the system. So what we do is we really lower the excitation power to 20 nanowatt. And in this case, now we see these narrow lines appears in the spectrum. And if we zoom in one of them, the narrow, right, the width is really narrow, about 100 micro EV. So similar, these look like quantum dots now. But if we increase our excitation power to regular, like tens of microwatts, now we see this broad background come back again, and with this narrow line sitting on top. Okay. And we study these in different twist angles. For example, right, this sample is 20-degree twist. They have another sample, say 57-degree twist. We will see these narrow lines when we excite the system with really low powers, and they become broader when excited with high powers. And we can do temperature-dependent measurements. So these narrow lines will actually, right, will disappear at a high temperature. So these consistent with these thermal dissociation effects. So all the measurements we show here basically shows we do have these quantum dot-like, right, interlayer exciton photoluminescence. But even myself, when I first see these, right, I told, we were not convinced these from from Moiré potentials, because the simplest explanation will be, well, these emission coming from defects, right? They just look like defects. So how do we know they're not defects? They found actually Moiré potentials. So the first thing is we should go back to look at these valley-dependent physical properties, right? Because defects cannot give you valley-dependent physics. And let me remind you, for these valley-dependent physics, the first signature is we should look for these circular polarized photoluminescence. So we did that. And we excite the system with circular polarized light, and we do this polarization resolve photoluminescence. As I show you here, we do observe very strong circular polarized photoluminescence in the samples. And this is consistent with these Moiré potentials, right? Because in this every high symmetry point, actually they have these 3-4 rotation symmetries, consistent with what we see the circular polarizations. But that's not enough, right? We check these with different twist angles. For example, we have here with 57, 20, right, 2 degree, etc. And each sample shows circular polarizations. But there's a distinct feature between different twist angle is, what we found is, the circular polarization is actually determined by the twist angles. For samples near 60 and a 20-degree twist, all the luminescence will show co-circular polarizations. But for the sample near 0-degree twist, actually we observe these cross-circular polarizations. So basically now this polarization, right, it's a circular polarization, it becomes a global indicator and only determined by the twist angles. If you imagine, right, if it's coming from these random defects, I mean, the polarization should be random and it should not be determined by these the twist angle of the heterobilayers. Okay, so this twist angle dependent circular polarization is the first, evidence shows we have these Moiré superlattice. So basically, as I show you, right, in these in the theoretical pictures, depends on which Moiré, which kind of Moiré structure as the minimal energy potentials in the systems, we can have the co-circular or cross-circular polarized selection rules. And our measurements are consistent with these pictures. And the second evidence I'm going to show you is based on these magnetic field dependent studies. Here I show you circular polarization resolved magnetophotoluminescence. And the data is taken at the 5 Tesla. So we observe, right, these sigma plus polarized emission and the sigma minus polarized emission with Zeeman splitting between them. Okay. And now the spectrum looks like a bit random because there's a lot of peaks here, right? So if I plot this PL as a function of a magnetic field, now we see this intensity plot, right? Looks quite regular. We see a lot of cross patterns, right? Each cross represents a emitter, okay? And even though some of these emitter has stronger than the others, if I don't know if you can see in the background, there's a lot of very dimmed cross features here, and all these features also has different energies. But there's one thing in common for all these cross pattern is, right, the slope are the same. Okay, so for these samples, basically all the emitter will show a G factor of close to -16, right? So this G factor is really uniform across the whole sample. And back to a few years ago, a group measured the G factor of another sample, which they measured one sample, which is a 51 tracer sample, and they measured G factor is also about a -15, very close to what we have in our system, right? The only difference is, they have to go to 30 Tesla to do this because for these free 2D exciton, the Linewidth is on the order of tens of millieVs. Then you have to go very high field to see reasonable splittings. The difference here is because the Linewidth we have is really narrow, only 100 microeV, so we only need a Tesla to see very clean splittings to extract these G factors. But what the consistent is, well, it seems like G factor is only determined by twist angles, and the consistent, is a narrow lines. The G factor is consistent with free 2D excitons. So these, because the G factor is determined by the crystal lattice, right? So this shows, well, the exciton, right, is trapped by Moiré potential, and it's consistent with its G factor is determined by the crystal lattice. And we can examine these G factor measurements in sample with different twist angles. And here I show you another example with theta is equal to 60-degree twist, and you see G factor is about -16, right? And I see another sample which is a bit mathy, but see that for 56 degree, but the one thing, well, we can still extract G factor is close to -16. So we can see the G factor actually is a very consistent global indicator between different samples, right? With slightly different twists, but only 60 degree. Now we go to the other extreme. We go twist angle with 2 degrees. Now you can see the G factor completely different, right? Now it's a 6.7 and with positive sign here. Okay, the sign also different. Now I go different twist with a 3 degree, and you see the G factor is 6.72, almost the same, right? And we test many samples. Basically, we can conclude we have only 2 G factors, and one is close to -16, and the other close to -6.7. And this G factor is determined by the twist angle. So without going into details, right? So we're going to show you the summary is, so near 0 twisted degree angles, right? The electron hole will have the same value index. Basically, electron will be, an electron and a hole, they will have the same value index, like plus plus or minus minus. And in this case, the value Zeeman splitting actually can be represented by this formula here. And here delta alpha is the value G factor difference between conduction and valence band. but the detail is not important. What it shows is, as long as the sample has a trace angle near 0 degree, they're going to have the G factor determined by this formula, and it gives the G factor 6.7. If the sample has a near 60 degree twist, so what that means is the value index of an electron and a hole is exactly opposite to each other. And what's the consequence of this opposite value index is, now the Zeeman splitting is determined by this formula here. Now it's 2 plus sigma alpha, right? Here, the sigma alpha is the summation of the conduction and valence band G factor. The reason is sum because, right, electron hole has different sign here. Okay, so this gives rise to the G factor is quite large, it's close to -16. So this gives us, what this tells us is, now the G factor of these narrow lines actually, right, this narrow line emission is determined by the trace angles. These also consistent with Moiré superlattice, because like I told you, right, the property of these excitons should inherit the crystal lattice structure, has nothing to do if defects, right, should not be determined by these trace angles. Now we go to look at another very interesting example is 20 degrees, right? In a 20 degree, we can do the same measurements. Then I can determine my G factor, which is close to -16. It's almost, right, the same as the theta equal to 57 degree samples. Well, although the 20 degree is far from 57, right? So what happens here? To understand this, we can look at the momentum space of these heterobilayers. Here, what I draw here on the left-hand side is MOSE2 electron layer, right? It's a conduction band. And for the WSE2, they apply these holes, okay? And I draw them in the momentum space, which is to the second Brownian zones. And the reason, I will show you in a moment. And then the color is coding is about the value index, right? For these red color means plus K value, and the blue is minus K value. Now we overlap these two electron and hole layer on top of each other. First, we look at these 0 degree twist heterobilayers, right? Then these plus K value of electron will sitting on top of plus K hole values. And also minus will sitting on top of minus. So we have value index pairing of plus plus and the minus minus. This gives us the G factor is about -16. Now we start to twist the sample, right? Go to 60 degree, roughly. And then you will see, right? Let's do it again. If you focus here, you will see this now minus going to go to on top of right? This plus K value going to sit on top of minus K, or minus K sitting on top of plus K. This value index pairing is plus minus or minus plus. This gives us G factor is about plus 6.2. Now let's go back. If we look at any kind of arbitrary trace angles, right? So is electron and the hole value actually going to misalign with each other? In this case, the photoluminescence will be strongly suppressed because it's a momentum indirect nature. But if we go back to look at the special angle, which is 21.8 degrees. So this actually is a commensurate angles. So what it means is if I rotate the sample around, 21 degrees, right? If it follow these, let's do it again. If we follow these dots, right? If we rotate about 20 degrees, you will see, well, this blue gonna sitting on top of red, or this red is gonna sitting on top of blue. So what happening is when we rotate a sample right near these commensurate angles, for the first Brownian zone, this electron and the hole value actually misalign with each other, so they don't really emit the light. But if we go to the second Brownian zones, now these electron and a hole are gonna sitting on top of each other, but with these opposite value index, either plus, minus, or minus plus, as a 60 degree trace angles, right? With that, so now we know why the 20 degree trace angle gives us the same G factor as near 60 degree trace samples. But there's a price to pay, right? Because the light emission happening in the second Brownian zones, they have to borrow the crystal momentum. So the process actually for theta 20 degree is Euclid process. Therefore, the light emission process is really inefficient. And we can confirm these, right, by looking at these luminescence in, taking the 20 degree and the 2 degree sample in the same conditions, right? The emission efficiency is about 2 order of magnitude difference. So with that, I will just summarize what I have, right? I have these more. I show you I have already trapped into the value excitons, And we confirm them is we have a quantum dot-like luminescence, we have strong value polarizations, we have trace angle dependent PO polarizations, and also trace angle dependent G factor. These give us a pretty convincing evidence we have these Moiré trapped excitons. So in the last couple of minutes, when I show you just some new development, right? The first is we have these gate dependent Moiré excitons. In this case, right, we can tune the charging in the system. So in addition to neutral Moiré exciton, now we can realize charged Moiré exciton, basically called Moiré trions. And we did the polarization dependent measurements, also magnetic field dependent measurements. Everything is consistent with these trion features. The second is the question I usually we should ask is, right, if these is really behave like quantum dot, can we observe these photon anti-bunching? And this is work done by Brian's group, and it's really beautiful work. And firstly, they found these cross pattern look like right Moiré excitons like we did. Then he focused on one of them and do these photon anti-bunching measurements, basically intensity correlation measurements. Then he do observe these very strong photon anti-bunchings, and at least confirms the single photon nature or trapped exciton nature of these Moiré excitons. And another question always we want to ask is, right, in the optical spectroscopy measurements, it's a far field measurements. So Jeremy just asked the question, right? How big is my beam spot? It's 1 micron. So basically, I cover many different traps, and I don't really know, the Moiré geometries really look like a hexagonal. All I know is I infer it from my polarization result measurements. However, so in order to understand what is really a correlation with this Moiré geometry to these Moiré excitons, right, in collaboration with Xiaodong, Abe, and Jim at the Columbia, they really lead these measurements. So first, what Abe developed is called piezo response force microscopy measurements, and to use this technique, we can image the samples, right, before the measurements. So here you show the sample really show this hexagonal lattice, and we also did the same thing in our own lab, and we do see these beautiful hexagonal Moiré superlattice structures. And with such samples, we can perform these polarization resolve measurements, and indeed they observe, right, these narrow lines and with circular polarizations. So this is consistent with what we did in our samples. But the new things, what they found is, well, in many different Moiré samples, what they found is actually, in addition to this hexagonal structure, they found also these one-dimensional stripes. So these one-dimensional stripes is mainly coming from these strings, right? When you have a strings applied to these Moiré superlattice, they become, basically the Moiré geometry will change to become these one-dimensional traps. And what they found is for these one-dimensional traps,
can we just
now
in a couple minutes?
Yeah, it's almost done. Yeah. So these one-dimensional traps, what they found is the PO length become really broad, right? It's not narrow anymore. This is number one. Number two is this PO feature is not a circular polarized, okay? They become strongly linear polarized, and the linear polarization is follow these stripe patterns. Okay? So the details you can find in this work just published a couple of weeks ago. So the key feature is by controlling some Moiré geometries, actually the Moiré exciton will behave very differently. And I'm gonna skip this one. I think the last thing I want to mention is the new development is, as I mentioned to you, right? We once with these Moiré superlattice potentials, you can start to trap these charges in these periodical structures, and we can use it as a simulator, just like people did in these atomic systems, right? And this work, the work is really advanced by from Wang's group at Berkeley and also Kim Van Mack at Cornell. They demonstrate, right, with this Moiré superlattice structure, they can load the charges one by one into these Moiré potentials and demonstrate, for example, mod states and Wigner crystal-like states. And just last night, right, there's two beautiful work appear online with Kim Van Mack, Jay Shine, and also with my friends Yongtao Cui, Su Fei, and Di Xiao. Each group, they show these beautiful insulating states. Right. Here, just example from Jason and the Kim Van Mack's group, right? You see many fractional charge states, and these type of states actually can be modeled really well. Here's the theory from my friend Di Xiao. So, the message I'm trying to say is, these systems actually really powerful, right? I think they're just a beginning, and we can really control these Moiré potentials and control the geometries, control the charging states, and to create all kinds of different mini-body states. So with that, I'd like to thank all the people who did the work and my collaborators, right? Di Xiao, Wang Yao, they did a lot of theory for this work, and the collaborator at Columbia, and also the Crystal Glory at the Oak Ridge National Lab. And the funding is supported by Department of Energy, and thank you for your attention.
Okay, well, thank you for a great talk. And let me open it up for questions at this point. We have plenty of time for questions right now. So
I have a few questions, David.
Go ahead.
Yeah, it's really amazing work. And so, I mean, so one question I have is with regard to the G factor. So is it isotropic, or is it really a G tensor? Have you tried to apply magnetic fields other than plane perpendicular to map out the G tensor?
That's good questions. And myself, right, we haven't done applied field in plane, but the other group did apply the magnetic field in planes. So what you do when you apply in plane? So you imagine, right, because these electron holes, they're sitting in different opposite values. So in plane magnetic field actually doesn't really do much because of the spin is pinned out the plane.
So it is. So
in plane field, it doesn't really do much work. What the in plane field are going to do is, for example, in the monolayers, right, they're going to start to basically create the coherent states between two different values, kind of rotate, like create a coherent states, sort of, yeah. But it doesn't really change the G factors. The other to say is that G factor is pretty much it's determined by the spin in the outer plane directions.
Yeah, so that's pretty interesting. So the other question is that, so if I imagine like these these quantum dots that are trapped in these in these Moiré superlattice, if you apply an in-plane electric field, I would expect to see polarization of the basically separation of the electron hole pair and a subsequent reduction in the photoluminescence intensity or increase in the lifetime. Have you tried those experiments, or do you see this kind of effect?
We tried to apply field in the outer plane directions. So in the outer plane direction, actually, we observe the exact same thing as you described.
No, but I meant in the in-plane
I know,
direction.
we haven't done in-plane. We tried, but that's a very difficult project actually because of the challenge. For example, right, when you say apply in-plane field, it means imagine, right, those are the really narrow, really thin samples, like couple nanometer. And there's challenge how to apply in-plane field by a couple nanometer in plane. But outer plane is much easier to do. You just need the two gates on top and bottom.
Well, I was just thinking like two side gates that are like 100 microns apart, and you just apply.
Yeah, way down those, it's very inefficient. You don't see anything basically.
I see. Okay.
But with outer plane, it's very efficient. And there's a paper already published too by Philip and his collaborators at Harvard. They also show when you apply outer plane electric field, they basically, it's not exactly move the electron a whole. You're not separating in some distance. What you do is when you apply outer plane field, you drive them out of these, you drive them into a context. So you can create the dissociations, yeah.
I see, but that's not necessarily what you want, right?
Well, I mean, it's similar effects, yeah.
I see.
Other questions?
So we also did trying to, there's other groups do, for example, right, you can try to create the in-plane drive current or other ways, try to push the exciton move in planes. We also done that. We can see actually exciton flows in plane, yeah.
I see.
But not separations. So the other think about it, this exciton, the band energy is not small. It's like 200 millieV.
Right.
Yeah.
Other people? Just going back, you're talking about the spot size is about 1 micron. You've got, so a whole bunch of these little valleys are being excited within that spot. So are these little lines, all this forest of lines that you get, is that really sensitive to exactly where you're focusing? So if you were just to move the laser spot slightly to the side, you would see a whole different set of lines?
Yes, exactly. You will see different set of lines, yeah.
Okay. So it's really very dependent on the exact buckling and the local potentials of exactly the shape of those traps.
Yeah, basically it's these things,
Yeah.
Yeah, it's these things. So they are really, they really varies in the space. Depends on, for example, just like it's a little buckling, right? You know, little strings or locally, they will change the Moiré geometry a little bit. Even though we cannot tell by eyes, but each trap, I would say they're slightly different.
Right.
So just like the quantum dots, yeah.
Mm-hmm. So I can go back to my question. So you said you tried the lateral gates and you didn't see. I mean, if you track, like if you're at 20, nanowatts excitation power, and you're looking at one of those exciton recombination lines, and you apply a lateral gate voltage, you don't see any shift of the line, nothing, because that's a pretty sensitive state.
So I didn't do the exact measurements. I did it for these Moiré excitons, okay? So I did it for 3 2D excitons. And what we see is, for example, when you apply these in plane field, right, there's a few things going to happen. The first is you don't know the effect is coming from the electric field or just coming from doping. Let me just give you an example, Look at these, right? The thing will shift dramatically just with a little bit of gate voltage. So it's hard to distinguish. That it's hard to distinguish. No, that's my point. That when you apply lateral gate, you're also having doping effects basically. Whenever you have a gate, you have doping effects. And it's hard to distinguish, these tiny little effects coming from like dopings or electric field effects, or just because of the homogeneity of the sample.
But the quantum dot itself, like you would know if you change the charge state on the quantum dot itself, because it would either disappear or radically shift.
That's a good point. That's exactly what I'm saying. We haven't done the exact measurements on Moiré excitons.
I see.
What I did is on 3 2D excitons. It doesn't work. Yeah.
Right. But I mean, so to me, this is a very interesting combination of things. So you have a very anisotropic G tensor, and you potentially have the sensitivity to lateral electric fields, and you may be able to suppress the recombination. So you could initialize, gate, and read out single electron spins using this system, which is pretty powerful.
Yeah, I think I know what you're talking about. Just like people did in quantum dots, right? Try to load the charging and take it out.
Exactly.
So that's sort of what we doing here. Not exactly as you say, but imagine, right? What I hear is I basically load one charging into it. You can see the lines, right? Shift to different parts. So I can load one electron, load one hole.
Yeah, with the anisotropic G factor, you can actually do universal gating. Like you can move all around in the block sphere.
Yeah, I understand what you're saying. Yeah.
Yeah.
That's what people did in these gate confined gallium arsenide quantum dots. Yeah.
I think to keep to our schedule, we probably need to move on. But again, all of you can virtually applaud for our speaker again. And really interesting stuff for follow-up conversations. But we have one last speaker, Nathan Youngblood, and is Nathan online?
Just follow that up.
Nathan is here. Okay, so I will read a short bio for him. He is an assistant professor in the Department of Electrical and Computing Engineering at Pitt. Was previously a postdoc at the University of Oxford, studying phase change photonics for non-von Neumann computing architectures. And his research interests include integrated photonics, 2D materials, high-speed optoelectronics, novel computing methods, and nanoelectronics. And so this will be a 15-minute talk plus 5 for questions. Go ahead. Thank you.
Great. Thanks. Thanks for the invitation to be here. And I just want to put out the disclaimer that this is not a quantum presentation, even though this is PQI. So I just want to make you aware of that, but I'm open to collaborations in the future if you think this would be applicable for quantum applications. So with that out of the way, I'm excited to share with you some recent results on a nanoscale memory cell that combines photonics, plasmonics, and phase change materials into a single device, which is able to store and convert information from the electrical to the optical domain and vice versa. This device unifies two otherwise incompatible data storage technologies into a highly compact and efficient footprint, while allowing direct comparison between the optical and electrical methods of programming. And I'll show how these devices can be used in the future for optical computation later on. So we live in a very exciting era of technological revolution brought about by advances in artificial intelligence. So if you've ever used Facebook's auto image tagging feature or used Google Assistant or Amazon Alexa, you've actually run a machine learning algorithm in the cloud. And these types of intelligent data processing services are very useful, but also very computationally demanding compared to the relatively simple task of data storage. Now, with the growth of 5G networks and Internet of Things devices, we need hardware that is able to sustainably scale with the increased computing demand of these new artificial intelligence services. And the issue of simply running machine learning algorithms is a huge challenge, but when we look at the amount of computing power needed to train state-of-the-art neural networks, the situation becomes much worse. So we are currently seeing a huge difference between the growth in computing demand versus the growth in computing efficiency at the hardware level. Now, in the past, artificial intelligence model complexity is roughly scaled with Moore's law, but within the last decade, there's been a huge increase in the amount of computing resources needed to achieve superhuman cognitive tasks, starting with AlexNet and kind of acute, resulting in AlphaGo 0. And these successes have been so far enabled by advances in multi-core GPUs, but simply connecting more and more GPUs together is not a sustainable solution for the continued growth of artificial intelligence. Now, this is because there's a fundamental issue in the way data is stored and transferred in most digital architectures. Most digital architectures have the data stored separate from the processor, which requires a lot of fetching and storing of data between memory, and that dominates the overall power consumption because we're charging and discharging these metal interconnects. This becomes especially inefficient and slow for common machine learning tasks like matrix multiplication, where matrix elements must be stored and retrieved from memory and brought into the CPU sequentially. Now, one solution to this problem is to reduce the operating voltage, but in conventional MOSFET transistors, this introduces the problem of leakage current, and that reduces standby efficiency. So if we don't address the flow of data during computation, in addition to making better transistors, the efficiency gains at the logic level will be quite limited. Now, the current need for very high throughput computing has led to a renaissance of optical computing research that was in vogue back in the 80s and 90s, but was largely abandoned because they lacked integrated photonics and photonics foundries. A major advantage of using optics to do computation is the ability to form matrix vector multiplications, Fourier transforms, convolutions, all those linear transformations that is really common in AI machine learning tasks. Additionally, optical interconnects can provide a lot of data transfer with very low loss using wavelength division multiplexing and very high bandwidth modulation. Okay, so to truly take advantage of computing the optical domain, we need devices which can efficiently store and convert information back and forth between both optical and electrical domains. And phase change chalcogenides such as GST are particularly promising for this due to their very large optical and electrical contrast when switched between their amorphous and crystalline states. These materials have also been industrially bedded like GST, which is shown to be very durable and reliable material both for optical and electrical applications such as rewritable CDs or 3D cross-point memory. Importantly, this material is also non-volatile and is stable at room temperature for decades. So my research focuses on the interaction of light with these non-volatile materials to achieve both data storage and processing in a way that addresses the need for very high throughput computation. So my research goal is really to achieve fast, efficient, and massively parallel computing using materials that are sensitive to both optical and electrical stimulation. Okay, so we've got a very promising material for both optical and electrical applications, but how do we control it? And the key is to really think of this material as a stable or as an unstable glass. So if we heat GST above its melting temperature and then rapidly cool it, we can essentially freeze the atoms in the amorphous state. So this causes GST to have a low optical absorption and low electrical conductivity. On the other hand, if we heat GST above its crystallization temperature and hold it there, we allow crystalline domains to form and the material will become polycrystalline. This results in high electrical absorption and high electrical conductivity, since we've transitioned from basically an insulator to a low band gap semiconductor. If we combine this with integrated photonics, we now have a powerful platform for storing optical data on chip. So to write data to GST, optical pulses can be sent to this to switch the state of the material between its amorphous and crystalline phases. And we can read out the state of a low power probe by determining whether or not it is highly transmitted or basically absorbed by the material. So this allows us to easily store multi-level data in the amplitude of, or the mixture of amorphous versus crystalline material just by changing the amplitude of this optical write pulse. Okay, so now we've got a material that is has great potential for integrated photonic memory. But we also know that the same material can be used to create highly compact electrical memory. So is there a device that we can make that really combines the best of both worlds into a fully mixed mode optoelectronic memory cell? This has been attempted by several groups over the past few years, and they've demonstrated ways of doing semi-mixed mode phase change memory, but each approach has had its limitations. And the only device that's shown here that can actually program and read out both in the electrical and optical domain is this VO2 device, but vanadium oxide is volatile, so you need continuous heating in order to maintain the state of the material. The reason that this is challenging to actually do in phase change memory is because when you switch the material between two electrodes, you actually form conductive paths, and those conductive paths prevent switching Joule heating from switching the rest of the material, so we only switch a very small portion. Additionally, if you try to make memory cells with electrodes that are too far away, much greater than maybe 100 nanometers in this case, you have to require very large voltages to actually switch this. So to make functional devices, you need electrical dimensions that are about 100 nanometers or less, which is quite small compared to the wavelength of light. But if we combine plasmonics, photonics, and GST, we can create a nanoscale memory cell that is fully addressable in both the optical and electrical domains. So this device, we've demonstrated, uses silicon nitride waveguides to couple to the plasmonic waveguide formed by two gold electrodes with GST bridging the gap in the center. This hybrid approach both reduces the propagation loss of plasmonics and enhances light interaction in the GST. Additionally, since we've reduced the switching volume of this material, both electrical and optical energy can flow through the same portion of material, which allows us to both read and write information in both domains. So our approach significantly reduces the size of the optical memory cell while reducing the switching energy needed to morphize the GST. Because of the strong field enhancement and the reduced volume of GST, we observe about a factor of 2 improvement, but that could be improved to probably another factor of 10 if we improve the coupling between the plasmonic mode and the waveguide mode. We were able to show both optical and electrical programming using these devices while simultaneously measuring the transmission and conductance in real time. Now, this is a very compact way of both storing data and achieving electro-optical conversion without necessarily using electro-optic modulators and photodetectors. Now, in the case of electrical switching over here, we see that the change in optical contrast is quite significantly reduced. And we attribute this to the different readout mechanisms between the optical and electrical domains and the fact that our nanogap is still relatively large compared to the minimum volume of material that can be reversibly switched. And this is kind of illustrating this point here. So if we switch a very, very small portion of material and we measure the resistance, we can actually break and make a connection in the electrical domain, whereas in the optical domain, we rely on the overlap of the optical mode and the volume of material that is in the crystalline versus amorphous state, basically. And this final experiment just kind of emphasizes this fact. So if we vary the optical pulses required to switch the material so we can store multi-level information, and we repeat this over multiple cycles, the optical domain is much more reliable versus the electrical domain. The electrical readout is much more stochastic, kind of indicating the stochastic nature of forming crystalline domains to rank and break that connection. So by combining multiple fields and strategies, we've essentially solved the mixed mode problem for multi-level memory applications. This device also allows us to directly compute the relative merits of optical and electrical phase change memory, such as switching efficiency, drift, endurance, and multi-level density, all in the same physical device. Now, in the last part of my talk, I'd like to briefly introduce an exciting application for these mixed mode devices, which we call photonic in-memory computing. And this idea is really inspired by recent work on analog in-memory computing architectures that use resistive memory elements to perform multiple matrix vector multiplications, or a single matrix vector multiplication in a single clock cycle. So we put input voltages and we change the conductances of these phase change memory cells, and we measure the currents, and we get an output vector from an input vector times a multiplication of this matrix. Now, doing the same thing in the optical domain could lead to a dramatic improvement in computational throughput. So how would we do that? Now, let's first address optical multiplication using phase change materials. So to do this, we would first set the state of the GST proportional to the number A, either using an electrical or an optical pulse. Next, you would send a second number B proportional to the input power of a second lower power pulse. And finally, you measure the output of that pulse, which is C equals A times B. And since the state of the material doesn't change because it's non-volatile, you can vary B as fast as you can vary the optical modulation speeds and measure the output C. So you can have very high speed multiplication happening using optical domain. So when we combine two of these cells together into one device, we have the basis for optical matrix vector multiplication. So we set the state of the GST, just a simple 2x1 matrix, and send another 2x1 vector. And when we measure the output, that's the result B, which results in both the multiplication and addition between this dot product. But how would we actually scale this beyond trivially small matrices? And to achieve this, we've developed a photonic crossbar array, which performs matrix vector multiplication on a 2D array of fixed phase change memory cells that can be individually programmed to store a larger matrix. So as an example of this, we show that we have 4 edge detection filters that we convert into a 4x4 photonic matrix and encode in these columns of this photonic crossbar array. And 4 pixels at a time are sent to the array, where the optical input power is proportional to the grayscale values of these pixels. And the columns implement multiply and accumulate operations, and the output of each column is the result of one convolutional step between the original image and the filter stored in memory.
You got about 2 minutes left.
Great. So a very cool feature of using optics rather than electronics to do this is the ability to multiplex computation in frequency space rather than in time. So in collaboration with Wolf Bernice's group at the University of Munster and Tobias Kippenberg's group at EPFL, we've demonstrated this multiplexing concept using an on-chip frequency comb shown here with hundreds of independent wavelengths as our broadband light source. Here we can use 4 different wavelength bands highlighted here to perform 4 matrix vector multiplications simultaneously in the same physical core. Now, these are some experiments that we did to show the same 4 edge detection filters, but computing the output 4 times faster because we're using 4 vectors at a time. I want to emphasize that the ability to do this classically is something completely unique to optical computing. The multiplexing ability and very high modulation speeds provided by optics could really be a game changer for applications requiring a very high computational throughput, because now we can use frequency as another dimension in scaling for computation. Okay, so to conclude my talk, I hope I've made a compelling case for phase change photonics in the field of data storage and computing. So in order to address current and future computing demands, we need to explore new computing architectures which go beyond sequential processing to parallel and even multi-parallel processing using in-memory computing techniques. Mixed mode devices like the ones I showed today could really bridge the gap between electrically reconfigurable memory and optical speeds and enable a completely new class of devices scalable to future computing demands. So if you're interested in learning more about this paper, we posted it on arXiv. And with that, I'd like to thank my colleagues at Oxford, where a lot of this work took place during my years as a postdoc before I joined Pitt, our European collaborators and funding agencies that supported this work. And thanks for your attention. Okay, well, thank you again, and welcome to Pitt.
So we'll open it up for questions. So again, we got about 5 minutes for questions from the live audience or from YouTube. So these this phase transition between the amorphous and the crystalline state, it would make me think that, you know, when it's easy to make things disordered and hard to make things ordered, right? So like, does it really become really crystalline? I would think that maybe disorder would accumulate over time after a lot of switching back and forth.
Yeah, that's a great question. So in electrical memory cells, they've shown cyclabilities. I would say 10 to the 9 in typical cells, and in some really highly modified cells, 10 to the 12 cycles. And they're not fully switching the material between its fully amorphous and fully crystalline state. So you actually have some crystalline domains that still stay there, and they kind of act as a nucleation site for reliable memory. So there's a burn-in period, basically. So it is a polycrystalline material when you crystallize.
Mm-hmm. What's the time scale for that transition? What's the, you know, what really limits the speed at which you can read and write?
Really the cool down time. So it really kind of depends on what you're using to switch the material. So you can use picosecond pulses or less in the optical domain, because you can heat up really efficiently with optical absorption. Electrical domain, it's more on the order of tens to hundreds of nanoseconds. So there have been demonstrations with less than a nanosecond pulse width for crystallization and amorphization.
Mm-hmm. Other comments or questions from the live audience here?
I have a question, Nathan. Very nice talk. It's kind of following David's question that you're mentioning that this phase change switching is basically thermally triggered physically, and also I think you mentioned there's the response or the on-off ratio for a electrical trigger versus an optical trigger is quite different. I think. Do you think it's related to the effectiveness of those two types of trigger in terms of generating heat, that enough thermal trigger for this change to happen?
Yeah, that's a good question. It is at the end of the day a thermal process. So you're heating up a glass, and you're either quenching it, so randomizing the atoms, or you're allowing it to form crystalline domains. And since it's such an unstable glass, those crystalline domains can form very quickly. So basically changing, the amplitude of an optical write pulse is enough you don't actually have to change the width. You can actually just change the amplitude to, either operate, bring it above the melting temperature or below the temperature. So you can use picosecond pulses to both crystallize and amorphize the material.
Right, and similarly, if you increase the current magnitude, you can achieve the similar thing.
Yep, exactly. Exactly.
Other questions? Okay, well, it's been an interesting afternoon. It's been great to have everybody here. And I don't know if the web people want to tell us anything about, do we just end it here, or do we want to go offline or stop recording, or any of the above?
We can stop recording, but for next week, well, thank you everyone that joined us today, Xiaodong and Nathan and Jimmy. I think Jimmy might have had to leave, but next week we'll have Daniel Stamper-Kern and Andrew Daly and Tom Purdy. Where's Tom? Yeah. So we're looking forward to it, and stick around.
Okay. All right. Well, thus endeth the official program.
Yeah.
Thank you.
Thanks, Xiaodong.
Thanks.
Okay, thank you.
Thanks, Jimmy. Thanks, Nathan.